Hello everyone. In this topic we are going to study about carbon and hybridization. So what is important about hybridization? Why should you study hybridization? Hybridization is a very important concept and it is essentially important because it determines bond strength, bond length and also the reactivity of different chemical compounds. So let us study in detail about what are the different hybridization states and how it actually influences bond length, bond strength and reactivity of a given compound. Now to determine hybridization, the first thing that you need to know is the electronic configuration. So here we are talking about carbon. So electronic configuration of carbon is 1s2, 2s2 and 2p2. Now if you write the ground state electronic configuration, the filling would be something like this. You can see that 1s2 it is completely occupied, 2s2 is also occupied completely and 2p is done according to Hund's rule. Now if we excite this from ground state, if we provide energy, essentially this electron gets promoted to an empty orbital here. And now you can see that the electronic configuration of the excited state looks something like this. Now what do you actually mean by hybridization? The word hybrid essentially means a mixing. Now here there is multiple, and we know that these are all orbitals which are singly occupied. Now there is a possibility of mixing. If S mixes with all the three orbitals 2px, 2py and 2pz, you essentially get sp3 hybrid orbitals. Now if the 2s orbital mixes with two 2p orbitals like 2s, 2px and 2py, and you have one 2pz orbital which is not involved in hybridization, then you have sp2 hybrid orbitals. Now if one s and one p combines, like here as you can see, and then obviously we have two p orbitals which are not involved in hybridization, and you get sp hybrid orbitals. So let us study in detail about what are these different hybrid states and what are their structures and their bond angles involved. The first hybridization state that we are going to study is sp3. So as we can see, the excited electronic configuration of carbon for sp3 hybrid orbital would look something like this, where s is actually combining with the remaining three orbitals here, 2px, 2py and 2pz, giving 4 sp3 hybrid orbitals. Now the structure of a hybrid orbital, we know that hybridization is a mathematical concept and the proposed structure looks like something like this. A typical example of a sp3 hybrid orbital or hybrid carbon is nothing but CH4 or methane. That is, it has all the four orbitals are satisfied by or are doubly occupied by hydrogen atoms here. So now we can see that CH4, four single electrons from hydrogen actually give completely filled orbitals, and the structure of this particular hybridization sp3 is nothing but tetrahedral. Now the bond angle involved in a tetrahedral structure is nothing but 109.5 degrees. So this is all about sp3 hybridization, and now let's go to the next hybrid state. The next hybrid state is sp2, which means s and 2p orbitals are involved. So here we can see that s combines with 2px and 2py, and there is one unhybridized orbital which also has one single electron. So these are the different sp2 hybrid orbitals, and because this has one single electron, it lies as far away from possible as from the remaining hybrid orbitals. So which is because electrons repel from each other, they have to be at maximum distance from each other, and in this case the structure will give something like this, which is nothing but a trigonal planar structure. What do you mean by planar structure? Planar is essentially lying on the plane, and here we have 2pz orbital, unhybridized orbital, which is above and below the plane. A typical example of sp2 hybridization is ethene, CH2, double bond CH2, in which each of the carbon is sp2 hybridized. So let us look at, an also important thing to remember here is what is the bond angle in a typical trigonal planar structure. It's actually a trigonal planar in the triangle form. It is 120 degrees. Now if you consider the CH2 double bond CH2, the hybrid orbitals would look something like this. So let's try to understand this in a little detail. Here we have sp2 hybrid orbitals where each of this is actually hydrogen, and we have two carbon, we have C and C, and which overlap linearly, giving us one sigma bond. So this is the one sigma bond involved, and now we can see that this is a double bond, CH2 double bond CH2, we have one sigma, and there is also a bonding that takes place between unhybridized p orbital. What is the unhybridized p orbital here? That is 2pz. So 2pz of one carbon overlaps parallelly with the 2pz of another carbon. So this is called parallel overlap, and when parallel overlap takes place, you get one pi bond. So it's very important to understand here that whenever we have double bond C double bond C, there is one sigma bond due to the linear overlap and one pi bond due to the parallel overlap between unhybridized p orbital. So this is all about sp2 hybrid state, and I hope you are very clear on how the orbital actually looks like. Our next hybrid state is nothing but sp hybridization. So what is S and P? Essentially means you have one s orbital mixing with one p orbital. So S and P will actually give you sp hybrid state. So how many p orbitals are remaining which is not involved in hybridization? We have two p orbitals which is not involved in hybridization, and obviously like in the previous case, they lie as far away from as possible from each other. So if you look at the coordinates here, you have x and y, you have two orbitals which are lying perpendicular to each other. Okay, let us try to understand how the hybrid orbital looks like in a given compound. But before that, we need to understand that here the overlap takes place linearly such that the structure of a particular compound, for example acetylene, that is Hc triple bond Hc, which is ethine, would be linear. What is the bond angle in a linear molecule? Obviously it is 180 degrees. Now to understand the hybrid orbitals of ethynes Hc triple bond CH, let us look at this particular figure. So here we can see that again you have one H, Hc bonding with another H, and we have two p orbitals which are unhybridized. Obviously we have one sigma bond forming between the linear overlap of C and C, and we have two parallel overlaps here, that is 2py combines with 2py of another carbon, and similarly 2pz combines with 2pz of another carbon. So here we can see that there are two parallel overlap which will give you two pi bonds and one sigma bond due to linear overlap. It's very important to understand that when we have triple bond involved, we have one sigma and two pi bond mainly due to two parallel overlap between 2pz and 2py overlap. So I hope you are clear on all the different hybrid states, sp3, sp2, sp, the different structures involved and bond angles involved. Let us try to understand hybridization by taking a few examples.